All right, so I guess we can slowly start welcoming you to this session. Probably in the next couple of minutes, people will still be joining, or so I hope. So thank you everyone for joining us. It's been a while since we do an SFP UQ student chapter talk. This year has been extremely weird for everyone, and us running the SFP student chapter have been quite busy and quite quite busy handling the changes in our research due to the pandemic. But we're very happy to restart the talks. And for these talks, as I briefly said in the invitation, we are going to invite a series of our recent graduates from UQ Fire to share a little bit of what they did in their PhD, the outcomes of their PhD, and also to tell us a little bit about themselves, and basically just see them in this new role. So they have a lot to share with us, and we will be announcing more talks very soon. And I hope that all of you can join us. And yeah, before we start, shout out to Vini and to Julian. Both of them have put a lot of work into making this happen, and the rest of the group of UQ Fire and everyone who has joined. And yeah, in the last few minutes, a few people have joined. So thank you everyone for being here. And yeah, I don't want to make this very long. So today we have Dr. Gerardo Soret, and he was recently in our group. He was finishing a PhD, and that PhD basically, and he will correct me if I'm wrong, but basically try to reconcile thermal inertia in the context of fire safety. So that's a very important topic. It's a topic I'm not very knowledgeable in, but I am aware of the implications it has in the design of the building envelopes, which is a huge problematic. So I'm very happy that Gerardo agreed to join us.
Teacher, I'm not.
Teacher,
I'm not trying to be rude, but your Zoom meeting.
What is it?
Your Zoom meeting got posted on a Discord now. Everyone can join. I'm just warning you.
Jaime, can you hear that?
Yeah.
Someone.
Yeah, I guess.
Yeah, this is one of the implications of not setting it as a webinar.
That's all right.
That's all right. So, great. Yes. So yeah, basically, we're gonna start, and yeah, the floor is yours, Gerardo. Thank you so much for joining us, and I'm gonna let you tell everyone about yourself and just go ahead with the presentation. So thank you, and we'll take questions at the end. We'll get to that later. Thanks.
Yeah. All right. Thank you very much, Jaime. So yeah. So as you mentioned earlier, so today, after a brief presentation of myself, I'm going to present the main findings and outcomes from the research that I conducted to achieve my doctorate degree. So along the presentation, you will find the references to the peer-reviewed articles available at the bottom of the slides. So yeah, I'm originally from Spain, where I got my bachelor's degree in industrial technical engineering at the Pontifical University of Comillas with the specialty in mechanics. Then I started my master's degree in materials engineering at the Complutense University of Madrid. I got access to the Erasmus program, and that allowed me to finish my master's degree in Belgium at the University of Liège. Back in Spain, I was working developing lightweight, modular, and actuated structures for climbing sports in MV+. And within the building industry, at Alfa Laval, working with building thermal comfort and refrigeration equipment, such as plate heat exchangers. All right, so once I got to Australia, I had the opportunity to start a PhD research project also related to the building thermal comfort, but to deal with very visible problems related to fire safety, which is what I'm going to present hereafter. I submitted my thesis report back in 2017, and since then I have been working as a fire engineer in QFES, in Queensland Fire and Emergency Services. So, as announced, my talk today focuses on the thermal inertia of building construction materials as a key parameter to assist the building component design decision process to achieve the best insulating properties, but also adequate flammability properties by following a holistic approach. But so let's put the building environment aside for a moment, and let's see how the thermal inertia is used in other engineering fields, because this will allow me to highlight some difficulties that can be found in the building environment to identify the thermal inertia. So what I'll do is I'm going to take you to planet Mars. So there are increasing scientific missions in planet Mars that use movable laboratories like this one, called Curiosity, to explore different aspects on the planet, as we all know. I think this is still operating now. So as anyone can imagine, these missions are very expensive. So the costs associated with any type of failure can be very high. Therefore, the team operating the rover from Earth needs to get reliable information that can assist their decision processes. For example, if we jump in the rover Curiosity and we look back, we can see the path followed by the rover. And then we can start wondering why the rover did not follow a different path to reach the current position. So why the rover did not follow an alternative path, for instance, on the right, or on the left? Was this decision made from visual inputs only? What is more, before operating the rover, where to land in Mars, right? So here we can see a high-resolution map of the surface of Mars. Imagine that we need to explore this area, right? So for instance, let's think about landing somewhere over here that looks like a flat and safe terrain to start, as it could sound reasonable. So again, should the decision be based only on visual information? Obviously not. There is a decision process behind that indeed rely on a more detailed and robust information. How can they get that information? What they do is use the thermal inertia of materials of the surface to evaluate the risk associated with the progression of the rover. In geophysical sciences, the thermal inertia is considered as a parameter of primary importance in the Earth and also in other planets, because the thermal inertia of the material composing the surface controls diurnal surface temperature variations. The thermal inertia of materials describes how sensible the materials are to temperature changes and combines three intensive material properties: the thermal conductivity K, the density rho, and the specific heat C. It is therefore a physical quantity. Thus, by measuring diurnal surface temperature variations on Mars, the thermal inertia of the terrain can be estimated and correlated with sand of different characteristics. Classifying sand by thermal inertia can assist the identification of sites that could be too slippery for the rover as areas with low thermal inertia. So this could enable the identification of potentially hazardous sand and avoid it before risking entrapment of the rover. So the estimated thermal inertia can be plotted in the map, and all in a sudden we can get a more detailed and robust information that assists the decision making process for both landing and operating the rover. And also we can understand better why all the missions on Mars landed where they landed. Every location can be found in areas where the thermal inertia is high. Interestingly, the mission here on the left, I'm not sure if you can see that, but is this yellow point here. And it's in an area with a low thermal inertia, and this mission ended up failing because the rover got trapped in an area with very loose sand beneath a thin hard layer on the surface where one of the wheels got stuck. So winter came, the rover became static and could not orientate solar panels during winter. With no power, the mission could not continue anymore and ended up dying. So, well, those having passionate interest about missions in Mars can visit the NASA website, which is down here, where you can get interesting information about also the route followed by Matt Damon as the main character in the Mars. Right? Okay, so we move now from Mars back to our planet Earth, where we find also very visible problems to deal with related to the building industry that at the end may require also very expensive solutions too. For instance, fight the greenhouse effect, reduce CO2 emissions, increase building energy efficiency, and all these dramatic facade fires that are happening here and there, where the cost would be also human lives. So at this point, we can think, can the thermal inertia of construction materials assist building design decisions? And if that is the case, how? Is the thermal inertia even used for building design purposes? So this is the topic of my talk today, thermal inertia as an integrative parameter for building performance. And I will focus on building thermal and fire performance. This is building envelope components thermal insulating properties and building components flammability properties. I will try to describe the problem first and then provide arguments that would enable these designers to deal with the problem. All this would take the form of the findings and outcomes of my PhD research, as Jaime mentioned earlier. All right. So with time, building envelopes designs are becoming more and more complex to achieve very challenging design criteria, such very strict energy efficiency requirements. And this includes both the design geometry and the construction material used. Here, we can see an example that presents all these aspects. I think that the name of this building is Bosco Vertical, and it's in Italy, in Milan, I think. So generally, the building envelope can be defined as the totality of components in a building that separate the indoor environment from the outdoors. Primary functions of the building envelope would be structural, weather tightness, thermal insulation, and associated energy efficiency issues, and fire safety. But there are others such as acoustics, buildability, and also the aesthetic aspect. All these functions are interrelated, and if they are deemed separately, then there is a risk to accept solutions that would be beneficial for one of or various building envelope functions, but will also be detrimental for others. So this would be the case if the designer would be putting a lot of effort to achieve high levels of building thermal efficiency, but is not evaluating sufficiently fire performance. All right, so, and this is the visible problem. Even though there were over 30 fires in the UK involving building assemblies, including high insulating and combustible materials in the 90s, in the last 20 years, there has been a dramatic increase of very visible building fires, facade fires, involving combustible insulating materials in the UK and all over the world, in particular in China and the Gulf region. Here, we can see what was called the first tower block cladding fire that happened in Liverpool in the early 90s. The fire spread vertically because the external wall system included insulating materials with very poor flammability properties, amongst other characteristics. So as a result, all the building levels were involved in the fire very quickly, breaching all fire compartments, and therefore the building occupants' life safety was fully compromised. The papers call this fire event the miracle of Knowsley Heights, a miracle. And here we can see after the fire event how a small group of firefighters are talking probably about the difficulties to deal with such a fire. So this is a type of fire that does not facilitate the standard operational procedure. Right? Yes, and we are all familiar with more recent fire scenarios like the one in the Grenfell Tower, similar in nature because of the massive use of light and combustible insulating materials, but with much more traumatic consequences. So the problem is still there. And to understand the problem from an engineering point of view, well, let's step back a little bit to revisit first the concept of insulation and the thermal models that describe the insulating properties of building envelope components. So to do this, let's use a lightweight prefabricated house that can be easily located whenever we want. Let's take a piece of wall and look at the interior. So this is a structural insulated panel made of two non-combustible MgO panels, one of each having an external cladding of a dark brown color plywood with a very thick insulating core material of polystyrene, together with a structural MgO spline in the middle. Right? So if we locate now this house suddenly in a place where the outdoor temperature is always much hotter than indoors, the internal heat transfer process that we could see in the cross section would be similar to that modeled here. Right. Okay. So after a short transient process, the heat would end up flowing through the system in a steady manner, and the temperature distribution inside would become linear. The proportion between the two would be the thermal resistivity or the R value. So higher R values deliver higher levels of insulating properties under this thermal condition, where it is quantifying the maximum amount of heat that can flow through the system. This parameter can be found in the building codes of here in Australia and also in the States. In Europe, instead of the R value, what is used is the U value in uppercase, which is simply the inverse of the R value. So we can also model the internal heat flow process of our prefab house or subject to a more realistic day and night type of cyclic temperature variation. Right? So, right. So now we can see that the internal heat flow process is significantly different. In this case, we can see that this in and out heat flow process with this cyclic period does not allow all the heat to reach the other side as it happened earlier under the steady thermal conditions. So this delaying effect would also participate on the insulating capabilities. Now, countries around the world committed to reduce CO2 emissions to fight global warming, and in this regard, the governments adopted very strict energy efficiency prescriptive requirements so that the use of heating and cooling mechanical systems would be reduced. In Australia, in 10 years, you can see here, the R value required double. Right? But the question is, are the Australian typical temperature conditions similar to a steady state thermal approach? Really? Is this model giving the Australian designers the right information to choose adequate insulating materials, enough flexibility? Well, we will get back to this aspect soon, I think. The steady state R value depends on two variables only: the thickness of the material, L, and its thermal conductivity, K. These other two aside are the interior and exterior surface resistance that are tabulated values and are not significant. So a thin slab with a low thermal conductivity could have the same R value of a thicker slab with higher thermal conductivity. However, the lowest levels of thermal conductivity are generally found on very light materials that are also combustible. So if we consider now robust analytic expressions to evaluate the specific flammability properties, we can get very important findings. Here we can see that the flammability properties such as the ignition delay time, T under IG, or ignition delay time, sorry, it depends very strongly on the thermal inertia of the construction material. Yeah. But we can see now that the low values of thermal conductivity would be beneficial to achieve strict R value requirements, but will also imply very short ignition delay times because, as mentioned earlier, these materials are usually also very light. So, in summary, these insulating materials have very low values of thermal inertia and therefore very poor flammability properties. So now we can see the real problem. There is a conflict of interest here. The questions would be, is there an alternative thermal model that provides thermal insulating properties where the thermal inertia is accessible? And looking for an integrated assessment approach. If we eventually extract the thermal inertia of materials from the alternative insulating properties, and we use it to predict reaction to fire performance, how valid would this be for design purposes? So we need to find a thermal model that first would provide more realistic description of building components thermal performance that would be compatible with the government commitments to improve the building energy efficiency, and also a model where the thermal inertia is accessible. Within the models used for predicting building thermal performance under transient conditions to achieve more accurate analysis, it can be highlighted the admittance method. Right? It's a method that was adopted by the Chartered Institution of Building Services Engineers, CIBSE, and it's proved to be popular with engineers because its calculation procedure is tractable by manual calculation. And it includes accessible thermal parameters to describe characteristic properties of building components widely used by the building industry. So the admittance procedure uses the characteristic parameters derived from the periodic solution of the Fourier continuity equation to estimate building indoor temperatures. Right? Then, if we build a series of two prefab houses similar to that described earlier, but with different building envelope systems in a way such that both achieve the same R value, and we put them on different locations in Australia, then we can measure the indoor temperature variation during the day and compare the outcomes and see whether by using a transient thermal approach, the design decision-making process would become better informed to achieve a better building thermal performance. So let's see what happens, for instance, in Cairns. To see the indoor temperature variation in both houses, we can plot the outdoor temperature variation that is available from historical records visiting the Australian Bureau of Meteorology website, which would be this line here. Right? The mean outdoor temperature, which is the flat one, and the thermal neutrality, which is the temperature at which people feel not hot, not cold, which is pretty much a comfort condition, which would be the one here. Then, well, we apply the admittance method to estimate the variation of the indoor temperature in both houses. And we can quickly see that they differ significantly. So same R value, but different thermal performance. So is the current prescriptive requirements enough to define building thermal performance? Well, interestingly, if we overlap here the countries at the antipodes, and we have a look at the traditional buildings in these countries located all along the Mediterranean Sea, we will find houses with very thick walls made of very heavy construction materials, where during the summertime you can always feel pretty comfortable conditions. Right? All right, so okay, there are methods based on a transient state approach, but well, the question again is, can we find the thermal inertia easily on it? Well, on the thermal performance environment, the thermal inertia of materials expressed in his square root value can be called heat penetration, thermal effusivity, and others like specific admittance. So different names for the same property that can lead to confusion. So it is possible to identify the thermal inertia if you know what to look for, but it is not called like that. Further, some authors relate the thermal inertia with the effective thermal capacity of building components, or simply the thermal capacity. So there is confusion about what the thermal inertia actually is. In the building thermal performance environment, the thermal inertia is identified by the research community as a complex phenomenon like this, and defined using a qualitative description of the effect observed in buildings subject to transient thermal conditions. Precisely, it is the effect of the thermal inertia on building thermal performance what is usually evaluated by means of quantitative insulating parameters and not the thermal inertia itself. Furthermore, the quantitative insulating parameters are manipulated in a way such that the factors are created and used instead. So the most common is the decrement factor, F, a non-dimensional parameter well accepted by the building design community that represents a key parameter to evaluate thermal response of buildings subject to cyclic thermal conditions. That is required, for instance, when we use the admittance method that I presented earlier. The decrement factor, or also called the amplitude decrement, is often expressed by this equation here, where the outdoor temperature amplitude is compared with the indoor temperature amplitude. If we dig a bit deeper on the definition of the decrement factor, what we find is the cyclic transmittance, the U value, but in lowercase. This is the ability of materials to transmit heat under cyclic thermal conditions, usually with a thermal period of a day. This is day and night temperature variations. The cyclic transmittance, when the period of the cycle tends to infinite, results the steady state transmittance, the U value, but with upper case letter, which is the inverse value of the R value, as I mentioned earlier. So I know that all these sort of names makes the theory a bit more difficult to follow, but well, it is what it is. So we dig a bit more, and we see that the cyclic transmittance is expressed in the form of a complex number, where it's basically have two parts. So a part which expresses the magnitude of the wave, and another part which expresses the phase of that wave. Right? So we can also see another parameter relevant to this model, which is the surface admittance, which has a similar expression to that of the cyclic transmittance. Right? Actually, the cyclic transmittance can be found also in the literature as cross admittance. So again, it's a bit confusing. We can see that both expressions depends mainly on two parameters. the cyclic thickness, tau, and the specific admittance, A. So here we can finally find the thermal inertia, the KROC. So yes, sorry, oops, is not it. So yeah, I mean, this is important. So yes, the thermal inertia is there, so we can find and controls the capacity of materials to transmit heat under cyclic conditions, which is a type of transient state. Okay, but if we want to use this value of thermal inertia to predict flammability properties following an integrated approach, how valid would this be for design purposes? This will be the next question. Yes. So yeah. So in the figure, we can see the evolution of the cyclic transmittance, the U value, with increasing the thermal periods here in a logarithmic scale of two building systems with the same steady state U value, but different weight, as I described it earlier, located in two prefab houses all around Australia. Generally, as the period of the thermal cycle tau increases, the cyclic transmittance U value tends towards, following this path, tends towards the steady state transmittance U value, the upper case letter. So we put it up here, right? For building thermal performance analysis, the period of the thermal cycle tau, which is of interest, is the period of a day, which is around 1,500 minutes more, I think it is. And is the first gray vertical color line. It can be seen that that both building systems have different cyclic transmittance values for this period, right? So in this period, we find here for the heavy wall system, and this point here for the light wall system. Now, typical characteristic times for a fire event are of the order of 5 to 10 minutes to a time flashover. So all life safety measures need to respond within that period. So from the perspective of the safety of the occupants, the time to flash over would represent well the fire time cycle, right? So we put it here in the line. If we compare now the periods of the cycle that we have here, both fire and insulating properties, we can see that they differ significantly, and by extension, the associated values of thermal inertia. The ability of materials to store heat makes itself apparent under transient conditions only. Then, if the thermal period is long enough, nearly steady conditions, then the thermal inertia associated tend to be zero, so very low values. So if we would be using these values of thermal inertia to predict flammability properties, such as technetium delay time, then the result would be very low too, almost zero. If we consider the cyclic period of a day, the value of the thermal inertia would be higher, but would still be always lower than the case of a fire time cycle. Then, using the thermal inertia obtained from insulating properties based on a cyclic period of a day would always be providing very conservative values of flammability properties. And that's it. I think this is the core of the research. Next would be simply to do it and validate this theory. For that, I developed an integrated assessment method of building components that I'm going to present now very briefly. I'm not sure how well I'm going with the time. Okay. So the integrated assessment method proposed in this study consists in predicting the ignition delay time of any building assembly with combustible materials using the thermal inertia measured from transient based cyclic insulating properties. It can be applied at early stage of design processes where no physical system is being built yet. However, a more detailed and realistic assessment can be achieved if samples of the building systems are built for testing to evaluate relevant aspects that may affect also strongly the performance, like potential construction imperfections. So the proposed integrated assessment method is composed of 4 main steps, plus a fifth to evaluate how conservative these predicted flammability properties are. First, we develop a numerical model that we can rely on to get realistic information. Then we use our model to calculate both the cyclic transmittance and the surface admittance of our building envelope system, from where we obtain the thermal inertia of the system that we ultimately use to calculate the ignition delay time for specific heat flux load conditions. This is a specific fire conditions. Right? So to develop a realistic model, we need to conduct a small scale thermal test first on a building envelope sample built for this purpose. Here we can see the structural insulated panel that we have been using all along this webinar. What we did is to measure the temperature time histories at different points in depth the system by using the thermocouples. Then we develop a numerical model with the same geometry of the sample tested in a way such that following an inverse method approach, we can end up matching calculated temperatures with the temperatures measured during the test. Well, by doing that, what we get is all the numerical fitting parameters that enable a realistic model. And these are, for example, the thermal properties of the material properties of the system. Right? So once all the fitting parameters are obtained, we now can use the model to calculate insulating properties under cyclic thermal conditions. The boundary conditions considered for the numerical model, along with the heat load conditions, follow a sinusoidal sinus wave, right? A sinusoidal, I'm going to say sinusoidal pattern. This is represented here, right? With this wave. For a single monolayer building system, where a heat flux load is applied at one surface denoted as number 1, right? Deemed isothermal conditions at the unexposed surface, which we call surface 2. Right? Generally, the amplitude of the net heat flow, the net heat flow wave decays exponentially as it passes through the material. Its boundary conditions in the model are assumed to be adiabatic over time, and an initial condition is also included as represented, which represent the sinusoidal heat load applied to the exposed surface with an amplitude A and a cyclic period tau, which is the period of a day. Right? Well, a total heat loss coefficient, HT, is assumed to be not time dependent and is applied to the surface exposed. The unexposed surface includes an isothermal condition, right? Which is expressed as the way here. The finite element model outputs would be both the exposed and unexposed surface temperature histories and the heat flow time temperature histories at a point of the system. Right? From this data, with the aid of an Excel spreadsheet, the wave amplitudes can be quantified to finally calculate the magnitudes of both the cyclic transmittance and the surface admittance at a certain point, in particular. So now we can plot on the geometry of the system, right, the values obtained for both the cyclic transmittance and the cyclic admittance at different points of the system. This enables all sorts of thermal performance analysis that would definitely assist the building design process. But what is of interest today is the thermal inertia. Okay? To get this, both the U value and the cyclic transmittance and the surface admittance calculated are assumed to be the characteristic insulating parameters of a hypothetical monolayer system. And under this approach, and by using a nonlinear system of equations, using respective analytical expressions that we have seen earlier, the cyclic thickness tau and the characteristic admittance A can be obtained. And from the latter, the pursued thermal inertia. Right? So again, we can plot the results on the geometry of the building envelope system, and we can start from there multiple type of analysis. So just for curiosity, as per the rover operating in Mars, I put also here the values of the thermal inertia, but expressed in their square root, so that we could compare with the thermal inertia mapping that we saw in Mars. And yes, we could even find similarities between loose and light Martian sand and polystyrene. Well, anyway, once the thermal inertia is obtained, then we can use it to predict fire performance. Right? So we discussed earlier that the predicted ignition delay time would be conservative because of the different cyclic periods related to both a fire event and thermal performance. So the research included a verification stage with a small reaction to fire test to evaluate how conservative is the integrated approach. So the small reaction to fire test consists on first thmeasuring the heat flux that the building envelope would be receiving by using this device. And once we've got that information, what we do is just to locate our wall sample at the same distance from the heater, from the burner. And what we do is just simply to measure the time. At the same time, and while the surface is heating, we are using we used an infrared camera just to be able to measure the temperature in the surface of the sample, so that we can estimate the critical temperature for ignition. That would ultimately enable us to calculate our values, our flammability properties. Well, I focused the whole presentation on one type of building envelope component, which was the structural insulated panel, but the research also involved a light steel frame system. So I put all the information that we've got here, right? But the important thing is that we can see that the calculated ignition delay times by using this integrated approach are definitely much lower than the flammability properties measured following this small scale fire test, right? So, and that is what is important. We were able to validate the theory behind, right? So, yeah, to conclude, as a summary, the conclusion will be simply that the thermal inertia can effectively connect fire and thermal performance evaluations, allowing for an integrated assessment approach of building envelope components. So we've seen that it's not simple just to get there in the building thermal performance space, but we can do that, right? And another big conclusion that I would like to highlight is that the thermal inertia extracted from thermal insulating properties delivers very conservative flammability values. And for design purposes, what we can say is that high values of thermal inertia would benefit both fire safety and thermal performance in geographical locations where daily temperature variations are the more relevant indicators. So this would mainly be those geographical locations that are close to the equator and far from the poles, right? So, and then the low values of thermal inertia would be detrimental for fire safety, but would benefit the thermal performance of buildings located in climates where outdoor and indoor comfort temperatures differ significantly. So yeah, this is it. So I'm open just to respond any question that the others may have.
Thank you, Gerardo. That was very interesting. And I would invite anyone with a question to open their mic or type in the chat box and send their question. Does anyone have any questions? Okay, I don't see any, but I do have a question. And while anyone else comes up with anything, I wanted to ask you. So in the process of actually selecting a material for an envelope, for a building envelope, how would this, like in practice, be applied? If you're, let's say, the fire engineer recommending a particular material, what would be the ideal way to carry out this integrated framework?
Well, the most important thing is just try to work towards a holistic approach. So the advice would be not to address the thermal performance of the fire performance separately. At least if you are not following an integrated approach, an integrated method as I described here, at least just to put both together and give the same importance to both, right? Because it's not only about the thermal comfort, but it's also about the fire safety.
And would you say that that's not common practice? It's from what I understand, it's more typical just to focus on the thermal comfort and the insulation properties, and then the fire safety gets analyzed completely separately from that.
Yeah, well, I would say that the evidence is there. I mean, the evidence is that we have plenty of buildings where, I mean, the materials used has been chosen focusing on getting higher levels of energy efficiency, right? So, so all these materials are not only very good thermal insulators, but also are very light. So they are very cheap. So there includes lots of benefits, right, in the building process, in the design process. But I mean that this is the evidence. So the evidence is that we've been witnessing lots of fires all around the world involving all these materials, and that demonstrates that I mean there's been so building designers has been focusing on achieving these strict levels of thermal insulation just to comply, right, with the code. So that is clear. And by doing that, well, they simply did not dedicate enough attention, maybe, for fire safety. So the result is obvious, right? Is what I presented earlier.
All right, thank you, Gerardo. Yeah, I agree with that. It's quite a challenge. We have a question from Julian Tonino. He says, thanks for the presentation. And he asks, what would be your ideal material wall panel selection for a location such as cairns, regardless of cost? And and then he asks as well for different locations, and if you consider the seasonal temperature variation in your study.
Yeah. Okay. Hello, Julian. How are you? It's been a while. So
It has,
yeah.
Gerardo. It's good to hear from you again.
Oof. So yeah, good question. So what would be the material? But that is the point, right? So the whole thing is about getting tools that would provide more information and that allow us just to make better decisions. So in the case I presented, you can see that during the day, oh, we can get there actually, because this is interesting as well. So here. So here we can see that outdoors there is very hot. I mean, in the summertime we can see that it's hot up there in Cairns, right? But in the nighttime the temperature is pretty low, right? So if we are in a house that is lightweight, we are going to feel very easily temperature changes, right? So if it's hot outside, it's going to be hot inside, and the same during the nighttime. If we and this, for instance, a lightweight house made out of this polystyrene ship system, right? If we, for instance, I don't know, we consider a CLT, a cross-laminated timber building, same geometry, right, but made of a heavier material. By using this transient analysis approach, what we get is this information. We will see that the same geometry in the same place is going to behave different. So during the day, we are going to feel cooler in the house, but during the night, it's going to be hotter, right? So then you, at least what you get is more information, and then you can start thinking, well, if this is the case, right, I'm going to orientate my house, for instance, in a way such that during the nighttime, I could get enough cross ventilation so that in the nighttime, I can get rid of all this heat easily, right? So the whole point is about getting more detailed information or reliable information to make decisions, right? This is the whole thing. It's not about what is better, it's about trying to write the right tool, right? And in this case, the point is just to highlight a problem, which is that the same, so that the codes are prescribing R values, right? And that we can see that the different buildings with the same R values behaves actually in a very different way, right?
Yeah. And Vinny has a question that I think follows on that. And he says, for the climates where low thermal inertia is favored and thus your ignition delay time is small, the designer must then treat the problem as an optimization between thermal comfort and time for ignition. And he says that he imagines that right now people will simply try to encapsulate the problem away. So yeah, I guess I'm not exactly sure what the question from Bini is, but what I take from that, the question that pops in my head is, how can you then optimize that? How can you find the right balance? Because the first step is what you say, to produce the information, to actually be able to be aware of the fire performance and the thermal performance. But then wouldn't there be a next step of trying to optimize that?
Yeah, well, I mean, that's right. So the whole thing is that by getting all this information, then we can start thinking, right? So we can start making decisions. So, and it's not only about, or at least just trying to find other solutions, right? As encapsulation or things like that, right? The problem I always keep in mind is that construction has always imperfections. So one can think, well, my combustible material is a hazard that is perfectly encapsulated. Right? But is that the case? Because and is it going to last the the life of a cycle of the building. I mean, there's many other questions, right, that have to be put together to end up having a complete solution.
Okay, thank you. All right, so anyone has any other question? Ian. Yes. So Ian says, how did you choose the heat fluxes for your that you applied for the ignition tests?
Yeah, good question. That was chosen. So the exposed material, the exposed combustible material was plywood. So what we did was just to choose heat fluxes that were not too far from the critical ignition of a timber, because one of the so what happens while you are heating or providing a heat load to this layer of plywood is that if the heat flux is very high, then the heat wave is not going to have time enough to pass through this thin layer of a plywood, and it's going to ignite as the material was a semi-infinite element, as we were doing test in the concalorimeter, right? But if we apply higher thermal heat flux, right, we are giving time for the heat wave to pass through this combustible layer, and part of the heat is going to dissipate through the next layer, right, through the MgO in this case, right? So the behavior is going to change. So the question is why we chose these specific levels of heat flux, and this is the question, the response. I mean, the answer is simply because just to test how in this particular system how the different levels or the materials that are behind the combustible material would influence the time to ignition. Right? I don't know if that's clear.
Yeah, and I have a last question. Are you aware of any framework or any regulation that is starting to consider these two elements together?
So by elements, I understand thermal
thermal performance and fire performance.
And fire performance. Well, I don't know. I don't know, but what I know is that so in one of the papers that actually I think that is this one down here, towards optimizing thermal performance of prefabricated hubs in Australian climates, this article included so in this article it was proposed, for instance, the inclusion in the code of another prescriptive requirement together with the R value, which was kind of an F value, with the aim of allowing for a more allowing for better or a more informed design decisions, but at the same time enabling the analysis of fire performance aspects, right? So that was the intent of that proposal in this paper. So anyone can visit that article and could find it interesting.
Okay. All right, Gerardo. Well, thank you so much. That was a very interesting presentation, and we're very happy to have you as the first speaker for this round. And I hope you join us in the next talks. And thanks everyone who stayed up until now, and everyone who left as well. We will be in touch about future talks. Next one will probably be in about 2 weeks. So we will be sending out the information very soon. And yeah, if anyone has any other questions, please contact us or Gerardo directly. And yeah, thank you so much everyone for coming. Thank you, Gerardo.
Thank you.